So let me say that the slides and videos of the talks are already online. You should use them. And next, we're going to hear from Sergey Bravyi about quantum error correcting codes.
Okay, so I realize that it's the end of the day and probably everyone is tired. So if you don't understand something, please don't hesitate to ask questions. And this will be introduction to the theory of quantum error correcting codes. As you probably know, quantum states are very fragile, and a qubit is a two-level quantum system which is supposed to be completely isolated from the environment. But in practice, qubit always interacts with the rest of the universe, and this severely limits its lifetime. So to implement large-scale quantum algorithms, we would need to extend lifetime of our qubits by many orders of magnitude. And basically, we have two options. One solution is simply try to build better qubits. And there was indeed a very remarkable experimental progress over the last decade. But perhaps there is a fundamental limit on how far this approach can take us. And today I will talk about an alternative approach, which is quantum error correction. And so what we are trying to do here is to encode our qubit redundantly into many qubits in a way that allows us to diagnose and correct errors caused by decoherence. And in principle, well, at least in theory, there is no limit on how far we can extend qubit lifetime using error correction. And the first quantum code was discovered by Peter Shor in late 90s. So Shor demonstrated that indeed, under reasonable assumptions, we can use quantum codes to protect qubits from decoherence. And besides, he showed how to perform gates on encoded qubits in a fault-tolerant way. So basically, this paper somehow removed the strongest objection to viability of quantum computing, which is sensitivity to errors. Quantum codes found applications in many areas. For example, quantum Shannon theory studies how to transmit quantum information through a noisy communication channel. What are fundamental limits on the transmission rate, and how different resources such as entanglement or classical communication can help us. And quantum codes have a very close connection to the theory of topological quantum order studied in physics. And basically, the main signature of topological order is ground state degeneracy, which is robust against or stable against perturbations. And quantum codes explain how this type of stability can be realized in nature. Quantum codes also give toy models to think about quantum gravity and resolve some paradoxes in black hole physics. But I'm not going to talk about this. And this is a very high-level picture of how quantum error correction is supposed to work. So we start from some state psi that we want to protect from noise, and say this is a single qubit state. And then a quantum code is basically a recipe of how to map this state psi to a multi-qubit code word, which I call psi bar. And then some unknown error happens. So we get corrupted version of this code word. And then decoding step tries to diagnose and correct the error. And hopefully at the end of the day, we get our original state psi back. And so in the rest of the talk, I will try to walk you through each step in this process and somehow instantiate all these steps. And let me start from the encoding step. And a quantum code is basically a linear subspace equipped with an orthonormal basis. And there are two parameters, k and n, that quantifies dimension of this subspace and the full space. So the code has parameters k, n if the subspace has dimension 2 to the k and the full space has dimension 2 to the n. So we can encode k logical qubits into n physical qubits. And x bar denotes basis vectors of this subspace, and you should think of x bar as encoded version of basis vector x. And here some words that you will hear a lot in this talk. So this linear subspace is called code space. Any vector contained in the code space is called a code word. And so I will be talking about errors. And an error is just some linear operator acting on n qubits. And it could be non-unitary. And this is somehow the central definition. So we say that a code, quantum code, detects an error E if matrix elements of E in the chosen basis satisfy certain conditions. So we require that all off-diagonal matrix elements are 0, and all diagonal matrix elements must be the same. At this point, somehow it's not clear how this definition is related to error detection, but hopefully I will clarify this in a few slides. So at this point, it's just a formal definition.
Does not depend on C at all.
Well, this x bar and y bar are basis vectors of C.
Oh, obviously X.
Mm-hmm. And let me just give you a very simple example. And this is a 4-qubit code encoding 1 qubit. And so these are encoded 0 and 1 states. So they are defined in terms of Bell basis vectors. So we have two orthogonal Bell basis states, phi plus and phi minus. And I will use a certain nice property of the Bell basis. Namely, it's not possible to distinguish phi plus and phi minus by looking just at a single qubit. Say if our error acts non-trivially only on qubit 1, then it has the same expected value on phi plus and phi minus. So it's not possible to distinguish these states by looking just on 1 qubit. And so suppose, let's say that our error acts only on the first qubit and acts by identity on remaining qubits. So we need to check with error detection conditions, the off-diagonal and diagonal. So this matrix element is 0 because the error acts trivially on the second Bell state. Somehow this picture is like a circuit, quantum circuit diagram that represents this matrix element. And so we get inner product between orthogonal states, phi plus and phi minus, so we get 0. The diagonal matrix elements of E are the same because E acts non-trivially only on 1 qubits, and I just told you that it's not possible to distinguish phi plus and phi minus by looking at only 1 qubit. If the error acts on, I assumed that the error acts only on the first qubit, but of course, by the symmetry, the same argument works for any other qubit. So basically, this code detects any single qubit error. And the way I define the error detection condition, it depends both on the code space and orthonormal basis in the code space. But in fact, this condition is basis independent. And one can easily check this condition. So the code detects an error E if and only if somehow this identity holds. So pi denotes orthogonal projector onto the code space. So we sandwich error operator between these projectors pi on the left and on the right, and we must get the code space projector up to some coefficient eta. And the proof is just 2 lines. So first of all, we can write code space projector as a sum of rank 1 projectors onto basis vectors of the code space. And then we look at this operator, and we get a bunch of terms. And you can see that all off-diagonal terms with x not equal y vanish because of this off-diagonal error detection condition. So we are left only with diagonal terms, and all diagonal matrix elements are the same. So we can just look at matrix element 0, 0 and take it out of the sum. So we get some complex number eta times the code space projector. So it shows that error detection condition is indeed basis independent. And now let me try to explain somehow its operational meaning and why do we call it error detection. Say suppose we start from some code word psi bar that lives in the code space, and then we look at a corrupted version of this code word. So we have 2 terms, with and without error. And A and B are some amplitudes. Now, the full space is a direct sum of the code space C and its orthogonal complement C perp. And quantum mechanics allows us to perform a measurement that distinguishes between these 2 subspaces. And depending on the measurement outcome, we apply either projector onto the code space or projector onto C perp. And let's assume that measurement outcome is a C. So we got here. Then this is our final state. And with a simple algebra, you can rewrite it this way. So here I use the fact that psi bar is +1 eigenvector of code space projector. And then we can use basis independent error detection condition that I just showed you to get rid of this operator. We replace it by complex number eta. So if measurement outcomes is C, then our final state is the ideal code word up to some normalization coefficient. But if the measurement outcome is C perp, then basically this outcome can only occur if in the presence of error. So if we just have ideal code word, this outcome never happens. So basically it means that outcome C perp detects an error. This is why we call the condition error detection.
Should we think of E as unitary? What do you mean by an operator?
It could be arbitrary linear operator acting on n qubits. I mean, it may or may not be unitary.
What is the most general space of operator? Like any matrix?
Yeah, it could be any matrix of size 2 to the n.
Sergey, what was the question? You need to repeat the question.
Oh, sorry. The question was whether error E is a unitary operator.
Well, generally, what do you mean when you say operator?
Well, it maps n-qubit states to n-qubit states in some way. But I will consider some, I will show you some examples of errors in a little bit. Oh, actually, here it is. Yes, so, I will express all error operators in a basis of Pauli errors. And for a single qubit, we have four Pauli errors: identity, bit flip X, phase flip Z, and combination of bit and phase flip Y. And for n qubits, we have 4 to the n different Pauli errors, and these are just all possible tensor products of single qubit Pauli errors. So on each qubit, we have one of 4 possibilities. And somehow the important notion will be the weight of an error. And this is just the number of qubits that suffer from non-identity error, like X or Y or Z. And basically what we will try to do is to find quantum codes that detect or correct all Pauli errors of small weight. And Pauli errors have several nice properties. First of all, they are self-inverse. So if we can diagnose Pauli error, we can undo it just by applying error twice. And then Pauli operators either commute or anti-commute. They form a group. So a product of 2 Pauli errors is again a Pauli error up to some phase factor, which we will mostly ignore. And we form a basis in the sense that any n-qubit error can be expressed as a linear combination of Pauli errors. Somehow this is more like a conjecture or assumption that somehow for realistic noise models can be well approximated by a linear combination of low weight Pauli errors. For example, if we have independent random error on each qubit and error rate is small, then this approximation is very good. Yes, and most of quantum codes are designed to detect low weight Pauli errors. And in particular, we say that a code has a distance d if it detects all Pauli errors of weight less than d. So this error detection condition should hold for any Pauli error e of weight between 1 and d minus 1. And I will use this shorthand notation for a code with k logical qubits and physical qubits and distance d. So, for example, 4-qubit Shor's code that I showed you has distance 2. And now let's somehow generalize this example to a distance 3 code. So it encodes 1 qubit into 9, and encoded 0 and 1 state are defined as shown here. So here we have 3-qubit cat states, and there are 2 orthogonal cat states that I call plus minus cat. Suppose we have some Pauli error E of weight less than 3, and let's try to check these error detection conditions. So the off-diagonal condition is satisfied because if error acts on at most 2 qubits, it must act trivially on at least 1 copy of the cat state. So this matrix element would be would contain inner product between ket minus and ket plus, which is 0 because these states are orthogonal. And diagonal error detection is satisfied because it happens that ket plus minus states have the same reduced density matrices on any pair of qubits. So it's not possible to distinguish them by looking at just 2 qubits. So this is completely analogous to the 4-qubit code that I showed you before. And of course, error detection is not very useful in practice because ideally we would like to correct the error, not just to detect it. And so let me explain how error correction works. Say, again, we start from some ideal code word psi bar. And then we get a corrupted code word, which is a linear combination of different errors. And let's say that each error here is some low-weight Pauli errors such that the code can detect it. And somehow we would like to perform some operation that maps psi back to psi bar. And as you heard from the talks this morning, somehow we can only implement unitary operators. So the most general operation that we can do is as shown here. So we bring in some ancillary register initialized in some state, say O0 state, and then we apply some unitary recovery operator that acts jointly on both registers. And ideally, we would like to get our initial code word in the first register, and the second register could be in some garbage state that we ignore. But this garbage state should not depend on psi, on psi bar. And by linearity, it's enough to see what happens for each term in this linear combination separately. Say we have some input state with error e sub y, and then we got some garbage state that depends on this input error. And defining property of unitary operators is that they preserve inner product. So if we consider 2 input states with some errors I and j, then and compute the inner product, it must be the same as input product of respective output states. And inner product of output states does not depend on encoded code word psi bar. So it tells us that somehow we can correct the error only if the matrix of inner products between corrupted code word does not depend on the code word. Yes, so this is what I just said. And let's assume that our code detects all errors of this type. So when we take a product of any pair of errors I and j. If this is the case, then we have this error detection condition, and we can compute this matrix of inner products between corrupted code words and use this error detection to confirm that it is independent of input code word. So somehow this error detection condition is necessary for error correction. And it turns out that, yes, it turns out that it's also sufficient. And this is known as a Neel-Laflamme condition. So if we have some list of elementary errors, E sub I, then the code can, quantum code can correct any error which is a linear combination of these elementary errors if and only if the code detects all errors of this type, like EI times EJ. And in particular, if we want to correct all Pauli errors up to some weight t, it is enough to have quantum code with distance 2t plus 1. Somehow it guarantees that all errors of this type will be detectable. But somehow having a large code distance is a very useful feature, but sometimes it's not sufficient. So there are codes that have very large code distance but perform very poorly for random errors. So let me clarify this point. So suppose we look at generalization of this short code. So instead of 3-qubit cat states, we can consider like multi-qubit, d-qubit cat states and define encoded 0 and 1 states the same way as before. Then it's not hard to check that this code has distance d. And let's consider a noise model that basically describes dephasing. So for each qubit, we do nothing with probability 1 minus epsilon, and we apply Pauli Z error with probability epsilon. And let's say that somehow we apply this dephasing channel independently to each qubit. Then it's not hard to verify that somehow this distance between corrupted 0 and 1 states decays exponentially with d. So as long as this error rate epsilon is constant, this distance is going to be exponentially small. And basically, using standard results from quantum information, this implies that it is impossible to distinguish with corrupted code words, except with exponentially small probability. So in the limit, then code distance goes to infinity, error correction would be impossible. Yeah, so it's I leave it as exercise to somehow prove this bound, and basically the calculation that you would need to do is to see what happens when we apply this dephasing channel to each qubit of a cat state, and then it shows that somehow after you applied this noise channel, the difference between cat plus and cat minus states is exponentially small. Yeah, so somehow what we learned from this example is that increasing the code distance leads to a sort of competition between error correction and error accumulation. So quantum codes with a larger distance can correct more errors, but they also have more qubits that can suffer from an error. And for the short code family, as we increase the code distance, error accumulation always wins. But there are other types of codes, such as the surface code. There error correction always wins as we increase the distance. And we say that such codes have error threshold.
Sorry, can you say exactly what do you mean by wins?
I just mean that as we increase the code distance, we must be able to correct error with probability close to 1. And I will clarify this a bit later. So increasing the code distance should make quantum code better than worse, which is what I mean. Yes, and there are certain codes known as quantum Ldpc codes, and they have a nice property that if you can show that the code family has growing code distance, this automatically implies that it has non-zero error threshold. And again, I will try to tell about this later, if time permits. And to define surface codes, let me briefly talk about stabilizer formalism. So we are going to consider a special class of quantum codes such that the code space is defined by these stabilizer conditions. So each operator S sub A is a Pauli operators, and code words must be +1 eigenvector for each stabilizer. And as I told you before, Pauli operators is a commute or anti-commute, and it's easy to check that this code space is non-empty only if all stabilizers commute with each other. So it means that, so it can be shown that this code space defined in terms of stabilizers is non-empty if and only if stabilizers pairwise commute, and the group generated by these stabilizers does not contain minus identity. So we can think about these stabilizer codes in terms of this abelian stabilizer group generated by stabilizers, and the number of logical qubits is simply related to the size of this stabilizer group, as shown here. For example, let's come back to this example of short code. So here I show a list of stabilizers, Pauli stabilizers that define the short code. So we arrange 9 qubits into a 3x3 square array, and then for each copy of the cat state, we have ZZ stabilizers on nearest pairs of qubits, and we also have these X-type stabilizers. So if you apply Pauli X to each qubit of the cat state, cat minus state, it would flip the sign. So if we apply all X to 2 copies of the cat state, we flip the sign twice, so we get original state back. So this is somehow alternative way to define this short code. Suppose we consider some stabilizer type code, and we have some Pauli error E. Then there are 3 possibilities. So the error can anti-commute with some of stabilizers, or it can commute with all stabilizers and contained in the stabilizer group. And the final possibility is that error commutes with all stabilizer, but it is not element of the stabilizer group. Then we have this error detection condition. In the first case, when error anti-commutes with some stabilizer, somehow it maps code space to orthogonal complement. So this product is just 0, and error detection condition is satisfied. In the second case, the error preserves the code space and implements identity operator on the code space up to a sign. So again, error detection condition is satisfied. And in the final case, error preserves the code space and implements some non-identity operator on the code space. So it means that such error is undetectable. Yeah, so in this error detection condition, eta could be arbitrary complex number. So basically it says that restriction of the error onto the code space must be proportional to the identity. And yes, it happens that somehow this condition is violated only in the third case. Yes, and the distance of a stabilizer code is a minimum weight of a Pauli error that falls into this third case. And there is a simple analytical formula for the distance, but I'm not going to show you because it's not very useful. In general, it's very hard to compute the distance of a quantum code. Yes, it's known that it's NP hard in a certain sense. Okay, and now I can define the surface code, and this is a stabilizer type code. So I can just show you stabilizers that define the code space. And here we have physical qubits that live at edges of two-dimensional square lattice. And the lattice have these rough boundaries on the left and on the right, and smooth boundaries on the top and on the bottom. And there are two types of stabilizers. For each plaquette of the lattice, we have X-type stabilizer, product of Pauli X over the boundary of plaquette. And for each side of the lattice, we have Z-type stabilizer, as shown here. And some stabilizers that are located near the boundary are truncated, like we have only 3x and only 3z. And you can verify that these stabilizers pairwise commute. So we define a stabilizer code. And this code encodes one qubit, only one qubit, and logical Pauli operators acting on these encoded qubits can be chosen as shown here. So these are strings of Pauli X and Z connecting opposite boundaries of the lattice. And so encoded 0 and 1 states can be understood in terms of cycles on the graph. And cycle is just a set of edges with the property that any vertex has even number of incident edges. And here I consider surface code with very large code distance, and logical 0 state would be a superposition of O0 state, when we don't have any cycles, and states with some loops. And we also may have paths that connects the left and the right boundaries. But the number of such paths, left-right paths, must be even. And logical 1 state is defined the same way, but the number of left-right paths must be odd. And somehow, if we have some Pauli error E, we define syndrome of the error as a set of all stabilizers that anti-commute with the error. Somehow this, let me show some examples. say suppose we have a single qubit X error on this qubit, then it would create syndrome at the two endpoints of this edge. And for some edges near the boundary, we would have just one syndrome, because this edge has only one endpoint. Oh, sorry. So remember that we define the code in terms of these stabilizers, and if we yes, so we use a Pauli operator in two different ways. So we use them to describe errors, but we also use them to define stabilizers of the code.
That's part of the code.
Maybe
Those X and Z's are part of the code, or
maybe it will help to clarify. I'm not sure it was stressed. You start from some Pauli operators. For example, X tensor X tensor X tensor X on 4 qubits, tensor identity with the rest. Okay? That's one operator. That's one stabilizer. Then there's another stabilizer, Z tensor Z tensor Z tensor Z. And the code space is just the space that consists of all vectors, which are eigenvectors of all the stabilizer operators with eigenvalue 1. That's the code space. And then what Sergey is now explaining is how this code behaves when you have errors, which are also X and Z errors. So it's confusing, but these are two different things.
Yeah, thanks for
Show again the diagram. I think this was a little bit too fast.
which one?
The one which will contain like what are the legal code words?
Oh, okay.
Yeah. What were the reds here? What does the logical zero means here?
Yeah. So this is just encoded zero state. So this code encodes one qubit into many qubits. So I just need to define encoded 0 and 1 states.
What's the diagram at the bottom?
Yes. Okay. So I was a bit fast here. So say this diagram represents the surface code lattice. So every edge on this lattice is a physical qubit, and so these red lines indicate physical qubits in 1 state, and black lines represent physical qubits in 0 state.
And this is a superposition over strings.
Yes, so we have a superposition of exponentially many terms like this. Then somehow we draw these loops. There are exponentially many ways to draw loops like this embedded into the lattice. But somehow it's more important to understand the code in terms of stabilizers, because it allows us to do error correction. And these diagrams are just for illustration.
While we're at it, maybe you can explain what's the importance of the fact that that an error commutes or does not commute with a stabilizer.
Okay. Yes. So basically, you should think of stabilizers as parity checks, like they are quantum analogs of parity checks for classical codes. So any code word must satisfy all parity checks. So this is analogous to saying that any code word is +1 eigenvector of every stabilizer. And then Pauli error happens, it violates some parity checks. So instead of eigenvalue +1, we get eigenvalue -1. And I'm going to explain this a bit later. Okay. Yes, so we define a syndrome of a Pauli error as a set of all stabilizers that anti-commute with it. Say X error creates either 1 or 2 syndromes on the endpoints of the edge. Z error creates either 1 or 2 syndromes on adjacent plaquettes. and Y error creates syndromes both on endpoints of the edge and on adjacent plaquettes. And it is important that we can determine syndrome of an error by measuring eigenvalue of each stabilizer. So remember that stabilizers pairwise commutes, so quantum mechanics allows us to measure the eigenvalues simultaneously. So initially, each code word is +1 eigenvector for any stabilizer, so it has a trivial syndrome. And then we consider a corrupted code word with some Pauli error. And if we measure eigenvalue of some stabilizer as A, somehow we can learn syndrome of the Pauli error. And this gives us certain partial information that we can use to correct the error. Yes. Okay, yes, sorry. Say this picture tells us that the error on this qubit would anti-commute with stabilizer located here, and it would commute with all other stabilizers. Does it make sense? So the stabilizer for this diamond would be a product of X along the boundary of this plaquette. And for this picture, stabilizer at this site would be a product of Pauli Z over all edges incident to this site. So again, it would anti-commute with X here. Does it make sense? Okay. Yes, by measuring eigenvalues of stabilizers, we can learn the syndrome of the error. And basically, based on the syndrome, we would like to choose some recovery operator, which is, again, Pauli type operator that corrects the error. So then we apply the error followed by recovery. We want to get our initial code word. And this happens if and only if the product of the error and the recovery belongs to the stabilizer group, maybe up to a sign. And this leads to a decoding problem. So we have some unknown error, but we know the error syndrome. And our job is to guess this unknown error modular stabilizers. For example, this could be error syndrome, and this could be one possible error that creates this syndrome. But of course, there are many other errors that create the same syndrome that differ by a product of stabilizers. Suppose this somehow with red dots, alpha, beta, and gamma represent error syndrome, and with red lines is X-type Pauli error. Then this would be one choice of recovery operator which is consistent with the observed syndrome. So if we combine the error and the recovery operator, we get combination of loops, and loops commutes with all stabilizers. So we come back to the code space. And this would be another choice of recovery operator. Again, it is consistent with the observed syndrome, but now a combination of the error and the recovery would be a path that connects left and right boundaries of the lattice. And in the first case, error correction succeeds because combination of error and the recovery is in the stabilizer group. But in the second case, error correction fails because combination of error and the recovery is a logical Pauli operator. So, and of course the question is how we choose the right recovery. And a good strategy is to choose recovery as minimum weight Pauli operator consistent with the syndrome. And more specifically, we first look at syndrome of site stabilizers and find minimum weight X-type Pauli operator consistent with the syndrome. Then we look at the syndrome of plaquette stabilizers and find minimum weight Z-type Pauli operator consistent with the syndrome. And then we combine two errors together. Yes, and somehow, in certain sense, this strategy is well motivated because we expect that actual error is more likely to have small weight than large weight. So let me again illustrate how this works. So suppose we observed this syndrome. Then at the first step, we will choose minimum weight X error consistent with site syndromes, which would be just single qubit X. Then we choose minimum weight Z error consistent with plaquette syndromes. This would be a 2-qubit ZZ. And then we combine errors together. So this would be our recovery operator. And as you increase the code distance, somehow it is important that as we increase the code distance, this algorithm can be implemented efficiently. And it can be easily reduced to finding minimum weight perfect matching in a graph. So we have a polynomial time algorithm for this problem. And for certain random errors, the running time, average case running time grows only linearly with the code size. So we can do this for thousands or maybe millions of qubits. And for concreteness, let's assume that we have random errors described by this depolarizing noise model. So for each qubit, we do nothing with probability 1 minus epsilon, and we apply one of Pauli errors, XYZ, with probability epsilon over 3. And we are assuming that we can perfectly measure syndrome of each stabilizer. Then, if you implement this minimum weight error correction algorithm, this is what you will see. So this axis is error rate of depolarizing noise, and this axis is probability of having a logical error. So the probability that error correction fails. So you can see that increasing the code distance somehow reduces a logical error rate exponentially if physical error rate is below certain constant threshold value, which is around 15%. But if the physical error rate is above the threshold, then increasing code distance makes things worse. This is for the surface code that I showed you. Somehow, if you want to use surface code to store quantum states reliably, our error rate must be below this threshold value. How much time do I have?
Half an hour.
Oh, okay, good. Yes, but somehow this depolarizing noise model is not very realistic because it assumes that errors on different qubits are independent. And now I want to discuss a slightly more realistic model, which is called local stochastic noise. And it was introduced in this paper by Aleferis, Gottesman, Preskill. So again, we consider system of n qubits. and random Pauli errors. And we say that a random Pauli error is local stochastic noise with error rate p if this condition is satisfied for any subset of qubits f. So basically it says that probability of that each qubit in f suffers from non-identity error decays exponentially with the size of f. So high weight errors are exponentially suppressed. For example, this depolarizing noise that I just showed you is a special case of this local stochastic noise. But somehow this definition is more general because it allows to have correlations between errors on different qubits. And I will use this shorthand notation to indicate that error E is local stochastic noise with rate P. And it can be rigorously proved that the surface code has a non-zero error threshold for this local stochastic noise model. So if we use this minimum weight error correction algorithm that I showed you, and the error rate is below constant threshold, in this case it's only 1%, then the probability of logical error would decrease exponentially as we increase the code distance. So this event fails means that the product of the error and the recovery operator would be a non-trivial logical Pauli operator. And the proof is very simple, so let me just briefly sketch it. And for simplicity, let's assume that we have only X-type errors. And so then basically we can identify an error. Sorry, this should be F. We can identify an error and its support. So this local stochastic noise condition says that probability of having an error on set of qubits F is at most this number. And by definition of minimum weight recovery, we choose recovery as X-type Pauli operator with the property that combination of error and the recovery is a cycle or a combination of loops. And a logical error happens only if this cycle somehow is non-trivial in the sense that it contains at least one path connecting left and right boundaries of the lattice. And by the union bound, we can somehow bound probability of logical error by this sum. So somehow each term corresponds to some path connecting left and right boundary, and we compute probability that this path is contained in the in this combination of error and recovery. And because somehow this recovery has minimum weight, we have this condition that if we look at this path H, then at least half edges in this path must be contained in the error. Because if this would not be the case, we could find a better recovery operator, which is a combination of R and H. So it would have exactly the same syndrome and a smaller weight. Yes, so then we can define a subset of edges F as intersection of error E and this path H. And again, we apply a union bound to get this upper bound. And then we use definition of local stochastic noise to bound this probability by this quantity. So it decays exponentially with the length of the path h. And for each path h, we sum over all subsets of edges f that contain at least half of edges of the path. And then with some simple combinatorics, we get this geometric series. And if error rate p is sufficiently small, this sum decays exponentially with the codistance. So we get this bound that I showed you before.
Can you also give a bound with n? I mean, does it also scale exponentially with n?
Yes, so n is approximately d squared. It's 2 times d squared. So it decays exponentially with a square root of n. Yes, so far I only talked about error correction. Then basically we just want to protect encoded states from noise and extend lifetime of encoded qubits. But of course, it would be nice to somehow to apply gates to the encoded qubits to perform some quantum computation. And logical gates are just n-qubit unitary operators that map chord space to itself. And in practice, such a logical gate must be implemented by a quantum circuit that consists of elementary gates like CNOT, Hadamard, and maybe a phase gate. And these elementary gates will be noisy. And somehow we should we should guarantee that our code can correct errors introduced by noisy implementation of this circuit. So we say that a logical gate is protected if such errors can be corrected. And first of all, I have to define what I mean. What do I mean by a noisy quantum circuit? Suppose we start from ideal quantum circuit like this one. Then the noisy version would basically obtain by inserting local stochastic noise after every layer of gates. Say E1, E2, and so on must be local stochastic noise. And for simplicity, I'm assuming that error rate is the same for every time step. And local stochastic noise has several nice properties. For example, composition of Pauli errors preserves the local stochasticity. So if we take a product of two local stochastic errors E1 and E2, it's also local stochastic noise, and the error rate goes up like a square root of p. And somehow constant depth Clifford circuits map local stochastic errors to local stochastic errors. And again, the error rate goes up roughly as a square root of p. And we can use these properties to aggregate all errors at the very last time step. Say we start from error E1, we propagate it through a layer of Clifford gates and merge with error E2.
Maybe say what Clifford gates are.
Oh, sorry. Yes. So somehow what is special about Clifford gates is that we map Pauli errors to Pauli errors. So if U is Clifford operator and E is Pauli error, then this guy is a Pauli error. And somehow if U is can be realized by constant depth Clifford circuit, then this guy would be a local stochastic noise. Yes, so we can aggregate all errors at the very last time step at the cost of increasing the error rate a little bit. So if initial error rate is P, then the final error rate would be this quantity. So as long as depth of the circuit is constant, this is a constant. And so this means that constant depth Clifford circuits are protected for any code that has non-zero error threshold for local stochastic noise. And I showed you that surface code does have a non-zero threshold. For example, suppose we want to implement a logical Hadamard gate. Then the first observation is that we can choose logical Pauli operators that are supported on the main diagonal of the lattice. Say product of all x operators along the diagonal would be logical x, and product of all z operators would be logical z. And if we apply Hadamard to every physical qubit, it would swap logical x and logical z, but it also would map x-type stabilizers to z-type stabilizers and vice versa. And somehow to undo this swap, we basically have to apply this sequence of swap gates that basically implements a reflection of the lattice against the main diagonal. Say this qubit would go here, this qubit would go here, and so on. And one can check that this circuit indeed implements logical Hadamard gate. Okay, this is what I just said. And this circuit has depth 4 if we express it in terms of standard gates like C0 and Hadamard. So the depth does not depend on the code distance. And there is a similar implementation, protected implementation of phase gate. And in fact, it only requires depth 1. And again, for logical C0 gate, we take 2 logical qubits, each encoded by a surface code, and then we apply a physical C0 gate for each respective pair of physical qubits. And this, one can check that this circuit implements logical C0 gate. Basically, this shows how we can implement protected logical Clifford gates. But to implement interesting quantum algorithms, we would need some non-Clifford gates. And I'm not going to explain the details, but basically there are some techniques how to do that. This is called magic state distillation. So basically the idea is that we can combine Clifford gates with preparation of certain single qubit states, and this would give us a computationally universal set of operations. And surface code allows us to implement logical Clifford gates reliably, and we can prepare noisy version of these magic states, encode each magic state by the surface code. So we would get a noisy encoded magic state, and then we would use logical Clifford gates to distill a noiseless version of a magic state. But unfortunately, this method has a very high overhead, so it's not quite practical. And there are some other ideas how to promote Clifford group to a computationally universal set of operations. And one of them is a code switching method. And basically, the idea is to combine protected logical gates of two different quantum codes. Say we could use surface code or some other code that gives us protected logical Clifford gates. And there are some other quantum codes, such as three-dimensional color code, that give us protected non-Clifford gates, like this T gate defined here. And then we would transfer logical qubit back and forth between these two different codes. And this somehow allows us to combine protected gates of two codes and achieve universality.
Okay, your definition of protected gate is just that there is an error threshold such that below that, when you decrease the noise actually after the gate, you get a better noise rate than before.
Yeah,
this is the definition?
Yeah, well, basically, the definition is that as we increase code distance, the probability of logical error in the gate decays, say, exponentially. But you can also think of protected logical gates as a logical gate that can be realized by constant depth quantum circuit. In a certain sense, these are equivalent definitions.
So if your code is LDPC, then you are not worried by this protection?
Yes, this is what is a nice property of Ldpc codes, that it's sufficient to have a large code distance, and it guarantees that we have non-zero error threshold.
So the study focus on kind of try to protect things, or try to design codes which are LDPC and not try to protect, what people are trying to do, more to do like LDPC codes, or more to kind of design general codes and protect them in some way?
I think people try to do both. Somehow this surface code and like related topological codes are more practical because we only require a two-dimensional grid of qubits. And with more general Ldpc codes, somehow they require long-range connections between qubits. So stabilizers of Ldpc codes are not somehow geometrically local on a lattice. Actually, this is the topic that I will discuss next. So what is quantum Ldpc code? And for simplicity, let me talk about stabilizer type quantum codes. So we define code space in terms of this Pauli type stabilizer operators. And we say that quantum code is Ldpc if each stabilizer acts non-trivially only on a few qubits, and each qubit participates only in a few stabilizers. So this is very similar to definition of classical Ldpc codes, if you think of stabilizers as parity checks. And somehow we quantify this definition using sparseness parameter. So we can draw this graph with qubits on one side and stabilizers on the other side. And we define sparseness of the code as maximum degree, vertex degree of this graph. And there are several reasons why people are interested in quantum Ldpc codes. As I said before, somehow if we can show that code distance grows sufficiently fast with the code length, this implies non-zero error threshold for local stochastic noise model. And there is important caveat is that somehow we don't know how to perform error correction efficiently for general Ldpc codes. So somehow the running time of classical decoding algorithm could be exponential in n. Then, because stabilizers of Ldpc codes act only on a few qubits, it's easy to measure syndrome of every stabilizer. Basically, it requires only constant depth quantum circuit. And again, if the circuit is noisy, then we would be able to correct errors introduced by noisy implementation of this circuit.
Sorry, I'm confused. We do know of Ldpc quantum codes with distance that behaves like that.
Yes, we have many examples like that, but not of these examples gives us efficient decoding algorithm.
There is a work of Zemmour where he can decode codes, no?
Yes, for example, surface code is quantum Ldpc, and we know how to do decoding efficiently.
But the decoding is not efficient, or it?
Well, for general quantum Ldpc code, we don't have efficient decoder. Yes, and also such codes give us toy models to think about this topological order that I mentioned in the beginning. And here I try to summarize previously known results. So here we have various code parameters, number of logical qubits, code distance, and sparseness as a function of code size n. So and the first line is the surface code that I just showed you. So it has sparseness 4 because each stabilizer acts non-trivially on at most 4 qubits, and each qubit participates in at most 4 stabilizers. And then the surface code can be extended to a hyperbolic surface, and in this case, somehow the number of we achieve constant encoding rate. So the number of logical qubits is linear in the code size. But the price we pay is that the code distance goes down. So instead of square root, we get a logarithm. And then, say, if we don't care about encoding rate and just want to maximize the distance, then the best known construction is certain three-dimensional hyperbolic version of the surface code, and the distance scales just a little bit better than square root of n. And then there is very nice construction called hypergraph product codes. So it achieves both constant encoding rate and square root scaling of the distance. And it remains a big open problem whether it's possible to find good quantum Ldpc codes that have both constant encoding rate and code distance scaling linearly with n.
What's the situation with the decoding efficiency for the hypergraph product codes?
Yes, so in general, I believe that we don't have efficient decoder, but if you start from, well, if you take hypergraph product of like classical codes defined on expander graphs, then there is efficient decoding algorithm. So in certain cases, we know how to decode these codes, but not always. Oh, actually, okay, that's the next topic that I'm going to discuss. Yeah, so, and probably it's the last topic also. Yeah, so this hypergraph product codes is a general construction, and it basically takes as input a pair of classical linear codes, and it outputs a quantum code. And if input classical codes are Ldpc, the output quantum code is also Ldpc. And there is this very nice simple relationship between parameters of output and input codes. So basically, the code length of the output code is n1, n2. The number of logical qubits is k1, k2. And the distance of the output code is at least somehow the distance of the worst input code. And oh, sorry, I don't have equation for the sparseness, but as I said, if input codes have constant sparseness, then the output code has also constant sparseness. And I will go very briefly through this construction because it's quite technical. But basically, you have to specify input classical codes by the parity check matrices. And these matrices have some dimensions. And we can assume for simplicity that all parity checks of input codes are independent. So then dimension of each parity check matrix is simply related to number of logical bits in each input code. And so the output quantum code will be of stabilizer type, and it will have stabilizers of X type, like Pauli operator of X type, and stabilizers of Z type. And so here I show how to define stabilizers of X type. So this equation basically defines a binary matrix, and each row of this matrix is a bit string, and we have to convert this bit string into Pauli operator by replacing each zero with identity and replacing each one with Pauli X. And then we have similar definition for Z-type stabilizers, but now we have to replace each one by a Pauli Z. And somehow we have to check that this quantum code is well defined. So X-type stabilizers must commute with Z-type stabilizers. And this is equivalent to checking that inner product between any row of X stabilizer and any row of Z stabilizer is 0 modulo 2. And well, if you do the algebra and compute this product, you can verify that this condition is satisfied. Okay, yes, and the sparseness of the output code is basically the sum of sparseness of the first and the second input code. How much time do I have? Maybe maybe it's a good point to stop then. Okay. Yes. So just a few open problems, and one problem concerns robustness of entanglement in quantum many-body systems. And basically here motivation comes from physics, and so we can convert any quantum Ldpc code to a Hamiltonian, which is basically the sum of all stabilizer operators. So the code space would be the ground state of the code Hamiltonian, and corrupted code words with some errors would be excited eigenstates. We know that code words of good quantum codes are typically highly entangled states. So in particular, we cannot create a code word of a good code starting from a product state by applying constant depth quantum circuit. So we can define a class of trivial states that can be generated by constant depth circuits, and we know that for some quantum Ldpc codes, ground states of such Hamiltonians are non-trivial. So we need super constant depth to create such states. Okay, this is what I just said. And then there is a conjecture that for certain Ldpc codes, all low energy states of these Hamiltonians are non-trivial. And by low energy, I mean energy less than some constant fraction of the number of terms in the Hamiltonian, say 1%. So if we want to create such low energy states starting from a product state, we would need a super constant circuit depth, like logarithm or maybe square root of n or something like this. And then there is a closely related conjecture which is called local testability. And basically it says that all low energy states of this Hamiltonian must be close in a certain sense to the ground state. So if we have some Pauli error that violates certain number S of stabilizers, then such Pauli error has weight at most some constant times S. And somehow this conjecture was introduced by Darit and Lior Eldar. Yes, and the conjecture basically is that there exists a family of quantum Ldpc codes that have this local testability property. And there are certain ideas how to somehow reduce local testability to this previous conjecture about non-trivial low energy states. Yes, so this is just a summary of all open problems about quantum Ldpc. We cannot say much about code distance. It would be nice to have some systematic methods of deriving upper or lower bounds on the code distance. We don't know if exist good quantum Ldpc codes. It would be nice to have efficient decoding algorithms for more general families of quantum Ldpc. And When people do numerical simulation of decoding algorithm, one problem is finite size effects. So to observe a threshold behavior like what I showed you for the surface code, what one would need to go to very large code sizes with maybe thousands of millions of qubits. And then we have these conjectures about robustness of entanglement that I mentioned. And just over the last years, there was a lot of progress on each of these open problems. So if you are interested, you can follow these papers for more details. And that's it. Thank you for attention.
Questions?
Are there any codes where the decoders are a mix of few states?
Yeah, the question was whether for some codes encoded states are mixed rather than pure states. Yeah, so there is a class of codes called subsystem codes, and these are like stabilizer type codes that I showed you, but they have some unused encoded qubits that do not store any information. And the state of these unused or gauge qubits is completely irrelevant. So it could be a maximally mixed state or anything else. So in that sense, code words of subsystem codes could be mixed states. Oh, yes.
What are the relationship between the quantum code and the code over finite fields?
Yes, so I believe stabilizer codes like surface code would be analogous to classical codes over binary field. And there is a subclass of stabilizer codes that are linear over field GF4. For example, the smallest distance-free code, which has parameters 5, 5, 1, 3, 5-qubit code, it is linear, GF4 linear. And I have not showed you this 5-qubit code, but yes, you can easily find it.
Any more questions? Okay, so let's thank Sergey again.